Hello everybody, and in this video we're going to be doing a biomechanical force vector analysis on this movement here, and we're going to include all the different things that we need to have in a free body diagram when looking at different forces involved in a movement. So the first thing that we need to do is we need to find a moment in time that we want to analyze. So that will be our free body diagram that we're going to work around. So for this movement, we're going to just pick the point here where he's about mid-range or midway through the movement. This is our free body diagram. So now we need to find out our first thing. And our first thing that we need to look at is our joint of interest. Joint of interest is going to be where the motion is occurring. So many of us know this as a bicep curl. Again, we know that the motion here is around the elbow joint. So our elbow is going to act as our joint of interest. And once we have our joint of interest as our elbow, we need to see two different things. We need to find out where is the movement occurring. We know it's in the elbow. Where in space is it occurring? And what is allowing it to occur in that point in space? Those two things are our plane and axis of rotation. So since we're moving in the sagittal plane, because the person has their arms by their side and they're moving, bending and extending their elbow, we know that's then occurring in the sagittal plane in this specific example. We know that the axis of rotation has to be medial-lateral because that's going to act as kind of a pivot point to allow for this movement to rotate about. And a little tip that we can use to remember our plane and axis of rotation relationship is that they have to be perpendicular to one another. So if we are moving in the sagittal plane, then if we want to figure out our axis of rotation, if we pretend we don't know that, well, we know it has to be perpendicular. So in that case, it must be medial-lateral. Versus if we just started with the axis of rotation, and we knew that that was medial-lateral, okay, our plane has to be perpendicular, so that must mean that we're in the sagittal plane. And whenever we're doing a free body diagram here, if we're trying to analyze different forces involved in a movement, we need to take the view of the axis of rotation. So to us, it's not going to look like an axis. To us, it's just going to look like a dot because we're looking straight through it. So that's why it appears like a dot. So that's how we know that we're picking the best view so we can analyze the different forces involved in this motion. Because we need to be perpendicular to those forces so we can see them occurring and we can see them acting around our joint of interest here. So sagittal plane movement with a medial-lateral axis of rotation, and that is the view that we are going to be taking it through the axis of rotation. So next step, we have to identify different forces involved. So the way that I like to start, and that will probably be best in most scenarios, is to start with the external force. The external force is going to tell us, well, we have to do the opposite of the external force. So then we could figure out our internal force later. So let's try to figure out our external force. Well, we know that this guy has a barbell in their hand, right? So how do barbells act? They act because of the force of gravity acting upon them, because they have mass and then gravity acts upon that mass, and that's what we use when we're exercising. So we're going to say our external force is not the barbell, it's the gravity, the force of gravity acting on the barbell. So once we have the external force, we know it's gravity. Okay, well, where is gravity acting upon for this motion to occur? Well, why are we doing this exercise? Well, we're doing it with a barbell so that we can make it more challenging for ourselves. Okay, so then we can say that our point of application, which is basically where the force is acting upon, well, we know that gravity is acting upon the barbell, so we can say that point of application for us of gravity will be the barbell in his hand, where the two meet. So again, external force, gravity, be most appropriate to say that it's acting against the barbell. So our point of application would be the barbell in the hand. All right, so now that we have the point of application, we need to represent this force vector as a force vector, right? It's not a dot. So we need to draw it as a line. And there's two things that we need to look at when analyzing a force vector, both for external forces and for internal forces. They have two characteristics that we want to look at. They have location and they have direction. So we're going to start first with location because we think it's a little easier to start with location. So when we're looking at the location of the force vector, or in this case, the red dotted line here, we're going to look where is it located relative to the axis of rotation. Again, so if we start at the axis of rotation and I need to travel to the external force vector, the force vector here, well, which way am I traveling to get to the line of force? Well, I have to travel in front of my body. So if I start at the axis of rotation and I want to get to the force vector, I need to travel anteriorly. Again, so our external force is located anterior relative to the axis of rotation. Again, that's important that we're relating it to the axis of rotation. And we can represent that here by this green line. You'll see here that the green line has like this 90-degree angle here, meaning that it's perpendicular, right? Okay, well, if we have a perpendicular line and it's between our axis of rotation and a line of force, that is going to be our moment arm. Because our moment arm is defined as a perpendicular distance, or the shortest distance, which is going to end up being perpendicular between our line of force and our axis of rotation. And then that's why we represent it here with this 90-degree angle. So if we want to find the location, we can just think, okay, let's say I'm a moment arm. Well, which way do I have to travel to get to the line of force? I have to stay perpendicular, right? So I can't travel up and at an angle because that wouldn't give me a 90-degree angle. I have to travel straight anterior in order to create a 90-degree angle and to maintain perpendicular. So here our location is going to be anterior relative to the axis of rotation. Again, that's very important. So next, we're going to look at our direction. You're probably thinking, okay, direction, we have to relate it to something as well, right? Yes. Our direction of our external force is not going to be relative to the axis of rotation. Our direction will be relative to the body. So to our person's body here in this movement. So, okay, we have this line drawn. So now we have to find which direction it's going to be pointing. Well, we know that gravity is always pointing down towards the center of the Earth, which I think is pretty obvious at this point. So we can see that the center of the Earth, or the ground, which gravity is also pushing us, pulling us down to the ground, is at this person's feet. It's pulling us down, has downward direction. So what's our fancy word for down? It's going downward, it's going inferior. All right, because that's the most fixed segment. Force vectors, we're going to have our direction being pointed towards the fixed segment. All right, so now that we have our external force identified as gravity, point of application was where the barbell meets the hand. We found out that it was located anterior relative to the axis of rotation, and then it has inferior direction relative to the body. And now we can determine what kind of torque it's producing. So we have a location and direction of the external force. Therefore, we can now say that gravity is creating an elbow extension torque based off its point of application. It tells us our location and also our direction. Those are all two things that we need to determine when we're trying to figure out what kind of torque a force is producing. All right, so those are all things for our external force vector. So this is why I like to start with the external force, because it just tells us, okay, we have to do the opposite of that, because that's why we're doing this exercise. So if our external force was generating a elbow extension torque, we have to do the opposite of that. So we're going to try to flex our elbow, right? So we're going to do that by utilizing our elbow flexors. We're going to look at the muscle groups as a whole, not just one individual muscle, because they're all working together. So our internal force that we identified is our elbow flexors, because we have to try to counteract the external force. So we can highlight our elbow flexors here in blue, generally attaching an anterior shoulder around the humerus and also on the proximal radius and ulna here, bones of the forearm. This is generally where the elbow flexors are located. So again, the first thing that we're going to do is figure out the point of application. The point of application, when we're looking at internal forces or muscles specifically, a little hint that we can use is our point of application for internal forces for muscles here. It's going to be the freest moving segment. So our muscles, they cross a joint, and the joint has two segments to it. In this case, the joint, the elbow here is the connection of the humerus with the ulna, and our radius is also moving. Well, relative to the humerus here, the ulna and the radius are moving more freely than the humerus. We have a fixed upper arm here, and our forearm is what's moving the most. So that's our freest moving segment. Okay, so we can say that our fixed segment is going to be our humerus, our anterior shoulder here with the origin of the general origin of some of the elbow flexors as well as the humerus. So our freest moving segment is going to be the insertion down here on the radius and the ulna. So we can say that our point of application, if we were going to use specific terms, is proximal, meaning closer to the body midline, anterior, it's on the front of the forearm, surfaces of the two forearm muscles here, the radius and the ulna. Again, if we're looking at point of application for our muscles, our internal forces, it's going to be the freest moving segment, where those muscles attach on the freest moving segment. So we have that here as the blue dot. All right, so our point of application was determined. So now we need to represent it as a force vector. So we have to have an arrow with location and direction. So we're going to start first with the location. So again, if we want to find the location, we have to think about the moment arm. Which way does our moment arm have to travel from the axis of rotation to get to the point of application? Well, if we had to travel between these 2 points and we had to stay perpendicular, we would travel anterior and superior. So our internal force is located anterior and superior in this exact moment in time. Again, if we were to analyze this with the barbell all the way down, we'd have different answers. But since we're using this specific point in time, our location here, the point of application, is anterior, because we're moving in front, and superior. Well, while it might be obvious that we're moving anterior, why is it that we're moving superior? Well, we have to analyze this, and if we were to do this using a better view, if we were to look at an x and y axis, with our 0 point being here at the joint of interest, our axis of rotation, we see that we're moving anterior. We do have a bit of an x, or a horizontal aspect, to the location of the internal force vector. We're moving anterior, but there is a bit of a y-axis, or a vertical aspect, to which way or where this point of application is located. So we're not moving straight to the right, and we're also not moving straight up. We're moving at a diagonal. So whenever we have a diagonal location, if we have to move diagonally, we have to use 2 different words to describe its location. So that's why we say that our internal force is located anterior and superior relative to the axis of rotation. All right, so we have location. Next thing to do is to find the direction. So again, a little tip that we can use is, if we want to find the direction of the internal force of the muscles, the elbow flexors in this example, we know that the direction is going to be towards the fixed segment. So remember that we had 2 segments. We had the freest moving segment that we found out was the forearm here, specifically our proximal anterior surface of the radius and ulna, which was our point of application. So our fixed segment, what was our fixed segment? Well, we know that we have the humerus and the radius and ulna at the elbow joint. So our fixed segment is going to be up the other insertion point of our elbow flexors, which is generally on the proximal part here of the shoulder. So if we have to have the direction directed towards the fixed segment, we're going to go up like this. We're going to point towards that fixed segment. In this case, it's superior and posterior. And we have, again, our force vector going indefinitely through space. It goes infinitely in both directions. Well, it travels in one direction, that's why we have the direction of it, but it goes through space infinitely. So again, we're using 2 words to describe it here. Why is that? Well, if we were to look at it as an x and y axis, or x and y graph here, we do have vertical aspect to the force vector. We're moving superior. That's more obvious here. We have to move up towards the fixed segment here at the proximal shoulder. We also are moving a bit horizontally. We're moving posteriorly. There is a horizontal aspect to the internal force vector. So since we're moving diagonally and not just straight perpendicularly, we have to use two different words to describe it. That's why we're saying superior and posterior. So, all that being said, we know that our internal force is located anterior and superior relative to the axis of rotation. We represent that by our moment arm here, again at 90 degrees between the line of force and the axis of rotation. And we have superior and posterior direction. Now we can figure out what kind of torque we're producing. So we figured out the location, direction. All that being said, we can now conclude that we are producing elbow flexion torque based off the location and the direction of the internal force vector. All right, so we can go ahead and put both of those force vectors together, and now we can look at the relationship between those different torques being generated and what happens at different points of the movement. So we're going to look at different types of contractions. So first we're going to look at concentric contraction. Concentric contraction is usually during the up phase of an exercise or a movement, whenever the muscle is getting shorter or the two insertion points are getting closer together. That's what we use to determine a concentric contraction. The muscle gets shorter, two insertion points get closer together. Whenever that happens, our internal force is generating more torque. We're producing more torque. So we're winning against gravity. So that's why our internal torque is greater than our external torque. So we're kind of beating gravity in this example. Whenever we move the barbell up towards our chest and towards our shoulder, the muscle is getting shorter, the 2 points are getting closer together. We are concentrically contracting the elbow flexors. Isometrically, what's happening? Well, isometrically, we break the word down, means same length. So there's not any movement going on. There's no change in length of the muscle. So we're not really bending or extending the elbow in that case. So whenever that happens, we have no movement. So that must mean that neither one or the other is winning against each other. So whenever that happens during an isometric contraction, we can say that the internal torque must be equal to the external torque, because neither one is winning against the other, because there's no movement. So now, if we look at the eccentric portion of a movement, or the eccentric contraction, that's usually the down phase of an exercise, or if we're going back to the starting position. That is when the muscle is lengthening, or the insertion points are getting farther apart. So if this person were to lower the barbell down to their thighs, the muscle is getting longer, the insertion points are getting farther away. Whenever that's happening, the external force is winning. Gravity is producing more torque than our elbow flexors. So there's more elbow extension torque than there is elbow flexion torque. That's why we extend into the starting position again. So eccentrically, we can say that the internal torque is less than the external torque. And that's true for any example, not just this one here. All right. So basically, here's a summary of all the things that we included in this free body diagram, doing a biomechanical force vector analysis of this person performing the movement. So the first thing we did is we looked at the external force. We figured out that it was gravity acting at the barbell in the hand. We found out its location, its direction, and then that told us what torque gravity was producing. We did the same thing for the internal force, because we know the external force tells us basically we have to do the opposite of that. So our internal force was our elbow flexors. We figured out the point of application being the freest moving segment, and traveling that way to get to the point of application from the axis of rotation, we described that as our moment arm, and that was our location, anterior and superior. And then our direction was towards the fixed segment, the same as gravity. Our direction was towards the fixed segment, the center of the earth. Our direction was directed towards the fixed segment, superior and posterior towards the shoulder, and that told us what kind of torque we were producing. We were creating an elbow flexion torque. So here is an example of all the things that we would include in a biomechanical force vector analysis, and we're going to include that in our free body diagram.